Yeah, so we will be presenting the 2001 IMO problem number 4. Unfortunately, Bo Q and Zhong Hao couldn't be here today, so we're just doing it. So the problem states that let n1, n2 to nm be integers where m is greater than or equal to greater than 1 is odd. Let x equal x1, x2 all the way to xm, and denote a permutation of the integers 1, 2, all the way up to m. Let f of x equal x1, n1 plus x2, n2 all the way to xm plus mm. Show that for some distinct permutations a and b, the difference f of a minus f of b is a multiple of m factorial. So first of all, we notice that for the set of numbers 0, 1, 2, all the way up to n factorial minus 1 is incongruent to f of 1, f of 2, etc. to f of m factorial mod f m factorial. Then by the pigeonhole principle, there must be some a and b such that 1, 2, all the way up to n factorial, such that f of a is congruent to f of b mod m factorial. Therefore, we must prove that 0, 1, 2, all the way up to m factorial is not congruent to f of 1, f of 2, all the way up to f of m factorial mod m factorial. So by contradiction, suppose that there was such a situation, then exists two sets such that 0, 1, 2, all the way to m factorial minus 1, and f of 1, f of 2, all the way up to f of m factorial mod m factorial have the same number of elements, or in this case, n factorial elements. For every t in the set of integers 0, 1, 2, all the way up to n factorial minus 1, there exists a v such that it contained within f of 1, f of 2, all the way to f of m factorial mod f m factorial, such that t is congruent to fv mod m factorial. So we set that, let that equal to t is congruent to f of v to the t, v subscript t mod m factorial.
So consider the sum of f of v0 plus f of v1 all the way to f of v m factorial minus 1 mod m. So because we know that we have t congruent to f of v of t for every v of t, so we can replace all those numbers with 0, 1, all the way to m factorial minus 1, and then that sum would be m factorial times m factorial minus 1 over 2. So another way to calculate it is to consider f of x as x1, n1 plus x2, n2 all the way to xm, nm. So we combine like all the n1s together, and then there are m factorial permutations and m terms. So there's m minus 1 factorial, like every element appears m minus 1 factorial times. So we have the sum equal to I times m minus 1 factorial for all I from 1 to m. And for all I from 1 to m, that is m times m plus 1 over 2. So the whole thing is m factorial times m plus 1 over 2. And because we have m is odd, m plus 1 over 2 is integer. So the whole thing, m factorial times m plus 1 over 2 is congruent to 0 mod m factorial. So we have m factorial times m factorial minus 1 over 2 also congruent to 0 mod m factorial. Also, since m is greater than 1, m factorial is even, so m factorial minus 1 is odd. So m factorial times m factorial minus 1 over 2, m factorial minus 1 over 2 isn't divisible by m factorial minus 1 isn't divisible by 2, so the 2 has to come from the m factorial. But then this has one less factor 2 than m factorial, so we have contradiction. So thus the sets from 0 to m factorial minus 1 and from f of 1, f2 all the way to m factorial, they can't be congruent. So we have AB such that FA is congruent to f of b mod m factorial, which implies that there exists some distinct FA and f of b such that FA minus f of b is a multiple of m factorial, which is what we wanted to show.